In this video, we're going to implement sensitivity methods for the propagation of derivative information over the solution to nonlinear systems of equations. For this, we're going to derive Jacobian matrices, as well as looking at finite difference sensitivities, forward mode sensitivities, as well as adjoint sensitivities. We can then execute the file in order to get a printout of the different derivative information as well as the timing, and then we will also see that the adjoint approach is the most efficient here. So let's get started. Hi and welcome to this new video. In the previous video we looked at adjoint sensitivities for nonlinear equations. Here we want to go one step further and look at nonlinear systems of equations. Those, for instance, arise when you discretize nonlinear partial differential equations or also in nonlinear optimization problems. Those kind of problems are given in terms of a residual function, which is a vector-valued mapping. So we will have a two-dimensional input to this residual function that's called x. So we have an x0 as well as an x1. And then this is a function which also maps to a two-dimensional space consisting of the residual in the 0th dimension as well as the residual in the first dimension. We can apply a root finding algorithm. One particular example would, for instance, be a Newton method in order to obtain the root to this residual function, which will be a two-dimensional vector, here given by x0 star and x1 star. And now we have the additional difficulty that this residual function is parameterized by a parameter vector theta. This theta has 4 different entries and they all appear here in this kind of arbitrarily selected residual function. And if that was a discretization of a partial differential equation, those could, for instance, be constitutive parameters that you want to fit, and therefore you might be interested in derivative information of a loss functional. So here we will look at a super simple loss functional, which will just take the solution to the root finding problem and will then square it. So it is an L2 loss against the 0 reference solution. And then we are interested in this aforementioned gradient. This gradient consists of 4 entries, since we have 4 parameters. And we want to have the sensitivity information with respect to all these 4 entries. And now we have 3 major approaches. I already mentioned them in the intro. There is an approach by finite differences. There is an approach by forward mode sensitivity analysis, as well as adjoint mode sensitivity analysis. If forward and adjoint sound a little bit strange to you, then I would advise you to look at one of the older videos where we derive the approaches in greater detail. So this will just be an implementation of those. In order to apply them, however, we need some additional derivative information. And for this, we have to take the derivative of the residual with respect to its 2 arguments. And it has the argument x, which is what the root finding algorithm is solving for, as well as theta, which is the parameter vector. So we have to take Jacobian matrices here. I've already derived them here by hand. It's a rather tedious task. You might also use a computer algebra system for that. And I just want to discuss the shapes real quick. So the derivative of the residual function with respect to the input will be a square matrix, which is 2 by 2. The Jacobian, however, with respect to the parameter vector, will be a 2 by 4 matrix, since we have 4 parameter entries. And it is 2 by 4 because we're using the so-called denominator layout. We chose that because that kind of simplified the derivations a little bit. If you had a numerator layout, that would be flipped. So then it would be 4 by 2. So don't get confused by that. On top of that, we also need the derivative of our L2 loss, but this is just the vector x. Well, then we look at our 3 different methods. First, finite differences. This is probably the naive approach. It's going to be the least efficient and also the least accurate. And in order to do that, we have to kind of loop over all the parameter entries and create an augmented parameter vector. For instance, if we wanted to take the derivative with respect to this theta 0, so maybe this should also be here, then we have to augment that entry with a small number. So usually this might be something like 10 to the minus 6. And then we compute the loss functional value without the augmentation as well as with the augmentation, and then subtract it, divide by this step length, and then we have an approximation of the derivative. The other 2 methods that we are looking at are precise up to machine precision. The first one is forward sensitivities. It will be more precise than finite differences, and it will also turn out to be faster than finite differences, although it still has the bad scaling property of finite differences, which is linear in the number of parameters. In order to make a forward sensitivity analysis, we first have to solve for the so-called solution sensitivities. For this, we have to solve a linear system of equations. This is in terms of the dx by d theta, so that is the unknown in that particular linear system of equations. The dr by dx is a Jacobian that we already have, so we have the functional form, so we can evaluate it at a certain position, and this particular positions are of course the solution from the original problem, so the x star, as well as the concrete parameter vector at which we want to get our loss sensitivity after all. Then we have a right hand side to this system, and this is the dr by d theta Jacobian, and as you see here, this is a 2x4 matrix. So it turns out that this is a batched linear system of equations. So we are not just solving it for one right-hand side, but we are solving it for 4 right-hand sides. So it should not be 6, but 4. And also here, of course, since we have to solve one linear system for each of the parameters. Consequentially, the dx by d theta will also be a 2x4 dimensional matrix. And this particular matrix, once we found it, then enters the evaluation, which allows us to get the dj by d theta vector, which is the one we are interested after all. And here I also want to highlight once again this negative scaling property, since if we had additional parameters, let's say 8 instead of 4 or 20, then we had to solve 20 systems of equations. I've already mentioned that forward sensitivities will still be faster than finite differences, and that is because for each parameter, this one only has to solve a linear system of equations, where the finite difference approach has to invoke the nonlinear solver once again. So for instance, the Newton method, which consists of multiple linear substeps and is therefore prone to be slower than the forward sensitivities approach. The adjoint sensitivities, however, are an approach that is constant in the number of parameters, and that is also seen here. The first step is to solve one linear system for an adjoint variable lambda that we have here. And as you see here, we need the dj by dx on the right hand side, which will always be a vector in case j is going to be scalar, but we are assuming scalar valued losses here. And that is of course highly advantageous, because if our parameter vector would be way larger, let's say 100, this would still only be one linear system of equations, whereas the forward sensitivities had to solve 20 or 100 systems there. Once we have the adjoint variable lambda, we can then evaluate the loss sensitivities with this equation. Then let's start with the implementation. So let me go below the doc string. Then first we're going to import numpy snp, and then we also need our root finding algorithms, and for this we will use SciPy. So let's say from SciPy import optimize, because there we also have root finding algorithms. Then let's create a main function, leave it empty for a minute, and then implement our main switch. So if name equals main, then execute the main function. And of course, there should be, name. Then go back to our main function, and the first step is to implement our residual function. And this residual takes 2 arguments, so it has the x, which is also the unknown where we want to find the root in, as well as the theta, which represents the parameter vector. I also want to leave this empty for a second, because I want to copy its definition down such that we can translate it easily. So I have that one copied. Let me paste it in here, move it in here, and then add some strings. So here we go. Then let's implement this. And for this, let us create a local variable called residual value. And this is a numpy array because, well, our function takes a 2-dimensional array and a 4-dimensional array and returns a 2-dimensional array. So let me use opening and closing angular brackets, and then let's translate it. So we have x axis at 0 plus theta axis at 0 multiplied with x axis at 0 minus x axis at 1, and then raised to the 3, and then plus theta axis at 1. This is the first row. Let's go on. And in the next row, we then have theta axis at 2 multiplied with x axis at 0 minus x axis at 1 minus theta axis at 3, and that also raised to the 3. Then let's return this residual value, and that's our residual function. Next up is to implement the Jacobians of the residual with respect to x and theta. That's a little bit of a tedious process, so I sped up the video footage here. And interestingly, this is also a process that is extremely error prone. So if you take these handwritten derivatives, if you've ever done that before, that's just like really tiring. And that is also a good point where you might want to use an automatic differentiation tool. And that's also what we're going to look at in the next video, where we, for instance, will use Jacs in order to automatically obtain these Jacobians to ease our lives. Okay, here we go. Now we have the Jacobians implemented. Let's use the Jacobians in order to create a function that solves the root finding process for us. And I want to call this function obtain root, and this one shall take a theta value. And this is kind of a helper function which calls the root finding algorithm from SciPy with a particular theta parameter vector and then returns the solution. So we will create a local variable I want to call root finding result, and this shall be given from the optimize.root function. And this one first takes a function. Well, this function is of course the residual, which we want to find the root of. Then we need an initial guess. And typically in those nonlinear root finding problems, that is really crucial to select a good initial guess, especially if the problem is multimodal, so if there are multiple roots to a particular residual. Here I just want to use a really simple initial guess, which is 2 zeros. So initial guess will be numpy array with 0 and 0. And that is just because here I don't want to focus too much on the problem of root finding, but just be advised that this is something that can become problematic. So let's add the initial guess. And also another crucial point is that if our root finding process does not converge, then everything we do thereafter with sensitivity methods will just be garbage. Well, then we also provide a Jacobian function to it. And this helps with certain algorithms because then this root finding method can use, for instance, Newton's method, which is highly efficient at these particular problems. And the Jacobian is, of course, the residual with respect to x, the one that we want to solve for. So this will be del r del x. And then, since the functions that we have here, so the residual function as well as the Jacobian functions, always take 2 arguments, we have to somehow build a wrapper or bind the particular theta value to the function call. And there is a convenient additional argument to the root method, which is called args. And if we create a tuple here with the theta value in it, then whenever the root finding algorithm is querying either the residual or the Jacobian, it will not only call it with the particular x value it wants to have the value for, but also with these additional arguments. And the reason I chose to use a root finding result local variable is because that is kind of a container with a lot of diagnostic information. For instance, we can figure out whether our root finding process was successful. And for this, I will just use a quick assert statement and say assert root finding result dot success, which will be a boolean that is either true or false. And based on that, we can then interrupt the execution of the Python file. And if that was successful, which we hope for, then we can return the root value, which we get by saying root finding result dot x. Let's make an example. For this, let's first define an evaluation point for our parameters. And here I will just select a relatively arbitrary one, which shall be evaluation point numpy array for parameters. For instance, let's take 1.0, -2, 1.0, and 1.2. And then we can, for instance, print the solution to obtain root on the particular theta evaluation point. And then let's execute the file to see what it does. And here we go. This now returns a 2-dimensional vector, which is the root to our problem. And we can also check that it is a correct root by, for instance, looking at the norm of the residual on the particular obtain root value. So I will just lazily call that here again. So basically what I want to do here is check how large the residual is at the particular root that we found together with the particular parameter vector we used in order to find that root. And if we execute that, and of course this should be norm, of course. So if we execute that, then we get a value which is really small, so it's 10 to the minus 23. It is not 0, of course. I mean, a root would technically be at 0, but with our machine precision, this is approximately 0. So the algorithm worked fine, which is great for us. So now we can continue. Next up is to implement the loss functional as well as its derivative. So let's define the loss functional, which takes the root finding result x, and then it just returns 0.5 times the norm of our root squared. Here we go, which will be our L2 loss. And then let's also define the derivative information, del j by del x, and this will simply be x. And then also for completion, we can execute this function once. So let's say print of the loss functional on obtain root on the theta evaluation point. And then if we do that, we get a scalar value that is the lost value. So since this is a rather abstract example, that's of course hard to find an interpretation for this, but think of it as following. We have a certain parameter vector theta, which we are then using in order to parameterize a residual. And then we are applying a root finding algorithm to obtain a root to the residual, which we are then plugging into a loss functional to obtain a scalar value. And obviously, if I change a value in this theta evaluation point, so let's for instance change the last value to 1.1 and then re-execute it, we of course also get a different result here. So let me change that back to 1.2. And then let's run it again. And then here we see that those two are different, so we get a different root value out, and obviously also the loss value is different. And this kind of motivates the idea that we are interested in this dj by d theta. So technically, where do we have it here? The derivative information of the loss on the parameter. Because we might, for instance, be interested in an optimization problem where we want to minimize or maximize the j value, and there this might be some gradient information. Or we are interested in local sensitivity analysis by saying which parameter affects the loss the most, because a high derivative value indicates a locally strong influence on the outcome. Well, and this is what we're going to do next with our three sensitivity methods. Okay, then let's start with the first one, which is the approach by finite differences. So let me go down here and say finite differences. And in order to perform finite differences, we have to set a step length. And a typical one, I already said that earlier, at least for double precision floats, is 1.0 times 10 to the minus 6. Then I will pre-allocate an array for the derivatives by saying dj by d theta finite differences is going to be at numpy dot zeros. Well, let's first figure out how many parameters do we have. Well, we know that, but I just want to make that more verbose by saying n parameters is the length of our theta evaluation point. So let's have our n parameters here. And this will create an one-dimensional array with 4 entries where we can then save the derivative information in. Then I also want to pre-compute the classical loss. And by classical loss, I mean the loss for an unaugmented theta vector. And I want to pre-compute that because we will then do an iteration over all the entries, and this obviously does not change. We're fine with computing it once. So let's do loss functional on obtain root and then the theta evaluation point. And I'm redoing the computation here because later on I then want to do a timing, so I want this to be part of the timing as well. Well, then let's do our main iteration for saying for I in range of n parameters. And then we have to augment the ith entry of our parameter vector. So let's say theta augmented is going to be theta evaluation point dot copy. And then we do theta augmented at position I. It's going to be plus equal the step length. In each iteration, we will take a copy of the full parameter vector, but we only augment one entry at a time. So this is the ith entry, because that's what we're then going to use to obtain the ith entry in our gradient vector. Well, let's do that. So we have our dj by d theta finite differences accessed at the ith position is given as the loss functional applied to obtain root on our augmented theta vector. and then subtracting the loss classical with the unaugmented theta vector, and we will divide that by the step length. And then this loop creates a derivative information, and we can obviously see here that this is a problem that scales linearly in a number of parameters, because the more parameters we have, the more iteration this loop takes, the more often we have to query this obtain root function, and this is the costly one. For large systems, this can take minutes or hours to obtain a root, and this makes this one a really expensive approach. Okay, that's finite differences. Let's now look at forward sensitivities. And for forward sensitivities, we also first have to perform a classical computation, but not for the loss, but rather for the classical x. I mean, here we would also obtain the classical x. I just directly plug that into the loss functional, but here we need the x classical. And the reason we need it is because we will soon evaluate residual and Jacobians, and this always takes x and theta. So this is a point at which we want to evaluate derivatives. So you will say obtain root on the theta evaluation point. Well, then let's look at the algorithm. And the first step was to obtain these solution sensitivities by solving a linear system of equations. So for this, we have to define the system matrix, which is this 2x2 Jacobian, as well as the right-hand side, which is a 2x4 Jacobian, and you can think of it as solving 4 linear systems for obtaining this particular 2x4 dimensional matrix. Okay, let's do that. And this brings us to the solution sensitivities. And here we will use numpy.linalg.solve, a high-level wrapper around a linear solver. And we will first provide the system matrix, which is del R by del X, evaluated at X classical and the theta evaluation point. And then the right-hand side is going to be minus del R del theta, evaluated at X classical and theta evaluation point. And if we look at the documentation of this solve, we see that it allows for B, so the right-hand side, to be either a vector with m dimensions or also an mk matrix where this k is considered as batched dimension, and it's not necessarily a looping as it does with the finite differences. It's kind of a little bit more clever because it can solve that at the same time. But conceptually, you can think of it as looping over all the columns of the right-hand side Jacobian and solving for them individually. Okay, then let's use the solution sensitivities in order to obtain the loss sensitivities. So this is a dj by d theta forward sensitivities, which will be del j by del x evaluated at x classical, transpose, and then matrix multiplied with the solution sensitivities. That's the forward mode. Let's go on to the adjoint mode, which is the one that we have all been waiting for. So adjoint sensitivities. And here as well, we first have a classical solution, and that is of course similar to the forward sensitivities, always in the theme that we have to do at least one classical computation whenever we want to use these sensitivity approaches. Then let's look at our algorithm. We will first solve one linear system for the lambda adjoint variable. So let's do that and say that the adjoint variable is given as the solution to a linear system, so linalg solve. And the system matrix is also going to be a del R del X evaluated at X classical and the theta evaluation point. But crucially, it is transpose. So it is swapped along the main diagonal. And that is because it is the adjoint of the matrix. And the adjoint of the matrix for real-valued matrices is the transpose of it. Then the right-hand side to the problem is going to be del j del x, evaluated at x classical, and then transpose. Here we don't have a theta in it because for simplicity for this problem I chose that the loss functional does not depend on theta. In general you can still have that though. Then let's use the adjoint variable to obtain the loss sensitivities. So dj by d theta adjoint sensitivities. And here we will get that by saying minus adjoint variable transpose and then matrix multiplied with del r del theta evaluated at x classical and the theta evaluation point. And that's already it for our three sensitivity methods. Let's make some fancy printout and print them all together. So we first have finite differences and then look at the dj by d theta finite differences. Then we will have our forward sensitivities, so forward sensitivities, and print the dj by d theta forward sensitivities. Then we will have our adjoint sensitivities, and there's a typo, let me quickly fix that. And here let's also print the sensitivities. And here we go. Then let's execute our file. And here we see we have three vectors, each with 4 entries. So we have a sensitivity with finite differences, forward and adjoint. And let's first compare forward and adjoint. And here we see those two are identical, at least to the digits of the comma presented here. And there's a good chance that given the root finding algorithm worked sufficiently, that those are highly accurate. So, I mean, they are dominated by the tolerance of the root finding algorithm, but here at least we can assume that those are quite correct. If we now compare them with the finite differences, we see that in most of the entries, they are getting into the right direction. So for instance, the first one in finite differences is 1.06 in comparison to 1.13. So that's okay. It's still pointing almost in the same direction, getting the order of magnitude right. It's the same for the second and the last. However, for the third, we see that there's a totally different value. And one particular reason for this could, for instance, be that the step length used for finite differences led the finite difference gradient to go into a fully wrong direction. I mean, not too wrong, it still has the correct sign, but it is definitely in the wrong order of magnitude. Let's now also compare the timings of these different algorithms. I again sped up the video footage because that's rather boring to see here. Okay, here we go. Let's re-execute the file. And now we also have timings here. So first for finite differences, so these timings are nanoseconds, but it's already fine to just compare the numbers here. Obviously there are changes between runs, and we'll run it again in a second. But here we see for finite differences, we have around 2 million nanoseconds, then 1 million for forward sensitivities, and around 670,000 for adjoint sensitivities. And that's kind of the pattern that we are expecting here, with adjoints being the fastest, then forward being the second fastest, and finite differences being the slowest. And that's of course because both forward sensitivities and finite differences have a scaling that is linear in the number of parameters. However, for the forward sensitivities, we are solving linear problems in each iteration, whereas the finite difference is solving nonlinear problems in each iteration. And if we were to increase the number of parameters, then the difference between the adjoints and the finite difference and forward would become more pronounced. So the adjoint method really shines when we have a lot of parameters. So let's re-execute it again. We can reproduce that, and you see overall we're still getting in the same direction. Sometimes forward becomes faster. I mean, one could do some statistics here, but I think overall I hope you believe me that the adjoint methods here are superior. And of course, feel free to play around with the source code file. You will find the download link in the video description, and also check out the next video where we will use JAX in order to obtain these Jacobian matrices automatically and avoid the manual labor aspect here. A big thanks to all the Patreons of the channel. If you also want to support my vision of free education on these advanced mathematical topics, you find the link to the Patreon page down in the video description. I hope you enjoyed that video. If you did, then please leave a like and consider subscribing to the channel. There's more awesome content like that on adjoint methods, automatic differentiation. Here you will now see similar videos as well as the playlist. I hope to see you in one of the next videos.